Hey y'all, many students fall for this trap. I did as well a long time ago, and I encourage you to pause the video, work through it on your own, see what you get, and then unpause the video and go through the solution with me and see if you fell in the same trap as many students did or not. And I'd be curious, let me know in the comments if you did fall for the trap or not. And if you did, that's fine, there's no shame in that, but you'll never fall for this trap again. This is a super common exam problem that we see all the time. So let's jump into it. Okay, so if you're here, then the first thing that most students do is they move this root 3 cos theta to the other side. So you got cos squared theta equals root 3 cos theta. It's kind of like an extra step. Just added this to the other side. Many students do that. And then we see a cos squared theta on the left and a cos theta on the right. So tend to cancel out cos theta. And you're left with 2 cos theta equals root 3, and then solve for cos theta. Cos theta equals root 3 over 2. And by doing this, we fell in the trap. Did you see it? This seems like it's right because it doesn't seem like we made any mathematical error, but this is wrong. By canceling out cos theta, we actually lose a solution. So I'm going to redo this, and rather than canceling out a cos theta, we're going to factor out cos theta. So we're left with 2 cos theta minus root 3 equals 0. And in this way, there's now two ways to get 0. Either cos theta could equal 0, or this other part, factor, can equal 0. And when you cancel out cos theta, we lose this solution here. So let's go through it. So let's find out what this solution is that many students lose. So we get cos theta equals 0. And to solve for this, we need to look at the interval of interest. And the interval goes from 0 to 2 pi. So we'll draw a unit circle, which is just a circle with radius 1. And to go from 0 to 2 pi, we're starting off at 0 right here. And 2 pi is 1 revolution around the circle. So it's 360 degrees is the same as 2 pi. Now to find out what cos theta is, we often resort to Sohcahtoa. So we have Sohcahtoa. Cosine equals adjacent over the hypotenuse. So this is equal to the adjacent over the hypotenuse. Now, where does that come in? Well, I'm going to just go over unit circle trigonometry really briefly here. If you imagine a radius on the circle, and then the angle is always with respect to the x-axis. The adjacent is the side that's beside the angle. That's not the hypotenuse. Here's our right triangle. So the right triangle is always made to the x-axis here. So this would be our adjacent. And the hypotenuse in a right triangle, in a unit circle, is always 1. So that's always 1. That means in order for this to be 0, this side here, which is our adjacent, has to be 0. And for it to be 0, that means we're pointing right on the y-axis. So we'll delete this here, and we're pointing right on the y-axis, so to speak. Now we can either point up or point down. And there's two ways to get this angle. So we start here at 0, and we move along to the first one. That's our first solution. The second one is we go all the way around until we hit the second one before the end of our interval. So theta 2. Well, if one circle is 2 pi, that means half a circle is pi, and a half of that is pi over 2. 90 degrees is pi over 2. So our first solution, theta 1, is pi over 2 radians, and theta 2 has to be pi plus another pi over 2. So that's 3 pi over 2. So theta 2 equals 3 pi over 2. Okay, so we got two solutions, and these two are two solutions that you wouldn't get if you fell for that trap. Let's look at the other two solutions. So we can have 2 cos theta minus root 3 equals 0. Make it in blue. 2 cos theta minus root 3 equals 0. So we'll add root 3 to the other side and then divide it by 2. So we get cos theta equals root 3 over 2. Now remember Sohcahtoa? Sohcahtoa. Adjacent, cosine equals the adjacent over the hypotenuse. Well, it looks like root 3 is the adjacent and 2 is the hypotenuse. And you could work it that way. There's nothing really wrong with that. But I like to relate things to a unit circle, and a unit circle has a radius of 1, or a hypotenuse of 1. The hypotenuse is always 1. So how can we make this so that it still has a hypotenuse is 1, adjacent over hypotenuse? And this can be 1. Well, we just make this whole thing the adjacent. So we have root 3 divided by 2, that's your adjacent, divided by 1. And that's the hypotenuse. This number is the same number as this. We can divide anything by 1. The adjacent is positive because the hypotenuse is always positive. So we have, this is some positive here. I'll just write A just so it doesn't get too messy. And the hypotenuse is 1, so this isn't to scale. There we go. That's 1. That's the hypotenuse. Now we could also go down as well. And if we go down, we still have a positive A. These triangles are supposed to look the same. It's just that my unit circle's pretty awful. But that's okay. We'll just kind of continue. So 0 to 2 pi. Now we got to go from 0 to 2 pi. Well, if we go up, first we have this angle here. I'll call this theta 3 because we already have 2 solutions. That's our first angle. And then our other angle is if we keep on going, we bump into the other one. So that's our theta 4. So we should have 4 solutions. Now, the adjacent is root 3 over 2. Hypotenuse is 1. Every time you see a root 3 over 2 or a root 2 over 2 or a 1/2, you want to think special triangles. And I'm going to go through these special triangles really quickly. If you want me to go in depth, just let me know. But there's 2 triangles that are special. And one of them has angles of 30 degrees and 60 degrees. The other one's 45 degrees. And we have these sides here, which is the sides we want. See, we have root 3 over 2 here. Well, this is similar. The triangle that we make is going to be just like this triangle here, where one side is root 3 over 2, the other side is 1/2. Hypotenuse is always 1. I have this in the description if you want to save it, look at it, use it, you're welcome to. Well, the angle adjacent to the side that has root 3 over 2 is 30 degrees, which is what we have here. This is root 3 over 2, this is the adjacent. So the angle that's adjacent to it, this is 30 degrees. So theta 3 equals 30 degrees. Now, in the question we were given radians, so we're going to convert to radians. We know that when we go around a circle once, we've gone 2 pi radians. We've also gone 360 degrees. So there's 2 pi radians for every 360 degrees when we go around a circle. Degrees cancel out. And if you plug this into your calculator, or you probably don't have to, 30 times 2 is 60, divided by 360 is 1 over 6. So we have pi over 6 radians. And the rad unit is often omitted. You'll see in exam. So if there's no unit, it's implied that it's radians. To get this other angle, what we're going to do is we're going to go around the whole circle, 2 pi, and then we're going to subtract this little amount right here. This angle right there. So theta 4 equals 2 pi radians, like we're going around the whole circle, and then subtracting this amount here. And this angle has to be the same as this angle because these triangles, even though it doesn't look like it because my drawing is so poor, but these are the same angles, or same triangles because they have the same hypotenuse is 1, they have the same adjacent, so they must have the same angle here. So this is the same as theta 3, which is pi over 6. So 2 pi minus pi over 6. Okay, so now if we solve for this, we need a common denominator. 12 pi over 6 minus pi over 6. So we're left with 11 pi over 6, and that's our other solution right there. So we got 2 of them. So our final answer is theta can equal, or the solutions are, we'll start at 0 and work our way up. So we'll hit theta 3 for the first one, pi over 6. The second solution will be up here when we get to 90 degrees, which is pi over 2. And then if we keep on going, we'll reach 3 pi over 2 for the third solution, 3 pi over 2, and then finally the last solution, 11 pi over 6. All right, hope you enjoyed it. You'll never get caught in this trap again now that you know it, and I'll see you in the next video. Cheers.